Hello, my name is Baillie and I am a domain expert in 5G and telecoms. I thought I would tell you about my 30-year journey in telecoms and my involvement with high-performance edge computing and its importance to 5G mobile through a short story. A long time ago, with the introduction of third-generation mobile networks and its data connectivity of just 384 kilobits per second, I was responsible for the development of a content platform. The need to render content quickly to the user was fundamental to the perception of quality of service. The inherent latency or delay for getting content to the device from the centralized content servers and the delays in the radio connection did not provide an ideal solution. I looked at a number of alternatives, but the concept of distributed computing techniques provided the best answer. By placing caches or data servers close to the radio access connection, content could be rendered faster and the size of the cache need only be dimensioned so that only the most downloaded or streamed content need be held. These content distributed nodes reduce the time to provide the customer content, but of course is asymmetric, as the majority of the data is downloaded with minimal need for upload. The content distributed network architectures are still in prevalent use today. Of course, there was still a need for the content to be held on the device with a lot of issues relating to digital rights management. Storing content on the mobile device meant that the device needed expensive memory chips, raising the cost of handsets and lowering adoption. So I moved to work on device design so that devices could receive content either streamed or downloaded. Streamed content needed less storage, but the limited bandwidth meant that the content needed to be cached before rendering to the user, and that required a temporary cache storage. Downloaded content required greater data storage. The whole of the content needed to be held and was therefore making the devices more expensive. Attempts to overcome the bandwidth limitations resulted in ideas such as downloading content overnight when the mobile network is acquiescent. However, the cost of storage chips meant a general move towards stream content, which we have today. I moved on to content billing, and since billing is critical to the customer service, I worked on large data programs for business support systems and operational support systems. Through the TM forum, I examined and designed the changes required in network to support the next generation of OSS and BSS, colloquially known as NGOS, required by the IP data telecom networks. Many of the systems needed to operate in real time and required high performance servers to analyze consumer data and feedback information such as how much credit does a customer have left on their phone. Through the new developments on OSS and BSS, I returned to fixed and mobile networks as they transitioned into IP data networks. I was responsible for some of the early fourth generation network deployments, and incidentally also for fiber networks, including fiber networks for backhaul to mobile radio sites or base stations, again with the focus to reduce latency and add bandwidth capacity to the mobile network. Early 4G suffered from a lack of devices, and although it did provide additional bandwidth compared to 3G, its multiple input and multiple output MIMO, what is now known as frequency spectrum slicing, was limited compared with 5G, which will support 10 gigabits per second with greatly increased slicing capacity. After 2 successful 4G launches, I returned to work again on devices. IoT devices are generally low performance with lightweight hardware and diverse access technologies, and not always mobile. IoT applications have increasingly generated large amounts of data. Therefore, the IoT requires a network computational platform, and to this end, the 5G Standards 3GPP group developed what they called edge computing, mobile edge computing. The design from the outset was to create a requirement for symmetrical data paths for mobile access and IoT devices. The MEC designation, though, didn't stick because it became the multi-access edge computing, drawing on the fact that as well as mobile apps and services, there were fixed network fiber apps and services that could be supported. MEC offers application developers and content providers cloud computing capability at the edge of the network. It supports a wide range of services such as video analytics, location services, IoT, augmented reality, content distribution, and data caching. 5G, though, provides a little more than just low latency and increased bandwidth. Software-defined networks and network function virtualization enable flexible architectures to create, distribute, and operate networking services. NFV uses IT technologies to virtualize mobile network functions, things like serving gateways, so they can be run on standard servers. It is not only the core OSS functions that can be virtualized, but also base station antennae functions that move the edge, literally, to the very edge of the mobile access network, and in fact are supporting the Open RAN standards. The concept of MIMO and spectrum slicing on the radio access can be extended into the core network, and software-defined networks offer the ability to establish secure private networks onto or in the core network. And this has led me to designing private mobile networks, especially for large industrial complexes. Data management for big data analytics has become critical. Retrieving large volumes of data poses issues to highly computational services and applications now at the edge of the network. Making use of such distributed computing requires the ability to store, manage, and access data generated at the edge, and to deploy, run, and orchestrate applications. So I am now back designing cloud data centers with distributed architectures, which is where I was 20 years ago with content distribution. Cloud data centers have been popular to store and access data for enterprises and applications. The benefits of lower storage costs due to scale, low bandwidth charges, high reliability and availability, along with co-location of applications, make cloud data centers attractive. However, IoT data and applications, 5G connectivity, and edge computing drive alternative data storage and processing strategies. The exponential growth in data having to be moved from the edge to centralized data centers will increase storage costs, require additional bandwidth costs, and increase latency. But not all data needs to be transported. Processing at the edge and moving the processed and valuable data to the centralized data center mitigates some of the disadvantages. This leads directly to placing more computational power at the edge. Indeed, why not now place the high performance computing located in the centralized data centers at the edge? It is more efficient, provides greater security for data storage, and minimizes network bandwidth. The existing architectures of ISPs and CSPs, with capital already deployed into the large data centers, are legacy systems that will have to be migrated in the future. But for new entrants, new adopters, enterprises who wish to capitalize on the benefits of the 5G revolution, they can avail themselves directly of the new dawn. So if you need assistance with developing your strategic approach, how your requirements can be factored into 5G and high performance edge computing operations, please get in touch as we can help you. Thank you for your attention.